everyone, my name is Leon. I'm going to talk about software-defined networking. And let's go. So the main goal of software-defined networking is to achieve open and programmable network so that we can develop or install application to do what it needs for common networking functions. As a result, network can evolve at the speed of software. Let's take a look at operating system on a common desktop computer as an analogy to help understanding SDN that I will discuss soon. So operating system can break down into three basic layers. First is the operating system itself. The operating system provides core services for the applications to manage system hardware on the lower level, for example CPU, storage, memory, and network interface, so that overall the system is flexible that can be customized to user-specific needs. We want the same level of flexibility within the network. And here is the SDN architecture. The middle layer for SDN is the network operating system, also known as SDN controller. South side, instead of hardware like processor, storage, and memory, we have network forwarding devices. The network operating system has core services for providing a programmable interface to the network applications. The north side still are applications, just like application on standard OS. This application can serve many purposes, but with SDN, they are of course network focused. The lowest layer are the forwarding devices. These forwarding devices can be traditional hardware switches as long as they support a programmable interface. Hardware switches support higher performance, while software switches provide greater flexibility for new behavior. The SDN controller needs a way to communicate with those forwarding devices. Type of information need to communicate include package handling instruction, alerts of packets arrival on network nodes, and notification of status changes, like links going up or down, and providing statistics information like flow counters. The most talked about protocol on the southbound interface is OpenFlow. The controller typically run with some core services include topologic service, inventory service, static service, and host tracker. Topologic service determines how forwarding devices are connected to one another and builds a topologic graph. Inventory service is used to track all SDN-enabled devices and record basic information about them. Statistics service reads counter information from forwarding devices like traffic counters and flow tables. Host tracker will discover where IP address as a MAC address of hosts are located on the network. The SDN controller provides application interface for the network application. It provides a simplified abstractions of the underlying network infrastructure. It is often sufficient for the entire network fabric to be represented as a single large switch for an application. And northbound interface commonly a TCP or UDP interface. And there's no standardized communication method here so far. So the application will gather information by the core services, and our application can serve a wide range of discipline. It can be, in effect, be whatever an organization requires in the context of controlling network behavior and implementing network policies. So when a packet arrives, the forwarding device will parse the packet header. It either already knows what to do with the packet or it queries the SDN controller. The network application will determine what action to take on the packet and push the information down to the forwarding device using the SDN controller as a translator. The forwarding devices will then take the assigned action on the packet. The forwarding device caches the instructions so that future packets don't require to check in the SDN controller. The same process continues device by device until the packets leave the SDN network to the destination or into a different SDN region or into a traditional non-SDN network. Future packet of the same type can take a fast pass without contacting the SDN controller based on the cache entry learned on the first time. This will last until the flow entry on the foreign device expired due to timers running out. So consider a traditional forwarding device. Traditional network node have data plane and a control plane both within a single physical system. Data plane is handle package based on the information stored in the table like MAC and ARPS table. Execution instruction in the data plane originated in the control plane. Control plane communicate with other nodes in the network by running distributed protocols like BGP, MPLS, and OSPF. Control plane determines how individual package type should be handled and push that information down to the data plane. Compared to SDN ecosystem, first, the traditional network node are a log box, which means the control plane is chained with the data plane. Both are coupled together in a single network node, and there's no direct access into behavior of the data plane to implement network policy. So the network operator most often configure the device through a command line interface so that if a new kind of network behavior is required, option can be limited. And for traditional data center, the disadvantage of traditional data center compared to SDN network is each network node is configured individually. Operator is not just dealing with a single point of configuration. In the traditional data center, there could be tens or hundreds of nodes to reconfigure to implement new policies. Each of its nodes has its own control plane. All of this control plane must communicate using distributed protocols. This traditional network paradigm is typically complex and can lead itself to configuration error. So back to SDN. There is a logically centralized controller with a global view of the entire network. Centralized control means there are no complexity of handling distributed protocol and configuring policy on hundreds of nodes. However, it is important to note that we can expect significant complexity to be present in the architecture of the SDN controller itself to accomplish all of its goal. So from the two extremes, they are centralized and distributed controller model. They require not only different infrastructure elements, but also offer different advantages and drawbacks. The centralized controller has a global view of the network. It ensures that the network is almost always in a consistent state and optimal configuration, and is more straightforward and easier to set up. However, it can quickly become a bottleneck in the large-scale deployment because all admin servers are handled centrally instead of locally, not to mention a single point of failure. As for the distributed controller, it offers significantly better scalability and latency since admin servers are running locally on each computing node and is highly available and prevent a single point of failure. The trade-off is the lack of global view as the synchronization between computing nodes to generate a virtual network topologic is difficult, let alone extra computation on each local host. Therefore, as a rule of thumb, we are always going with the hybrid, finding the sweet spot between the extreme. So to address the limitation in centralized and distributed controller approaches, hybrid controllers is introduced. It's a combination of both approaches to mutually complement their drawbacks. Controller can exploit the simple control of managing specific task data flow as in the centralized model while having a scalable and robust system in the distributed model. One critical challenge imposed by the hybrid model is to what degree the network abstraction should be centralized to support logically centralized control tasks, at the same time provide physically distributed protocol. The requirement to design an ideal SDN controller are scalability and performance and reliability. Scalability because the controller can quickly become a bottleneck when the number of connected forwarding devices initiate more flow requests than the controller capacity. And performance because every package flow needs to go through the controller during the flow setup process, so the controller should be capable of handling more traffic than end hosts. Lastly, reliability because SDN controller is just such a crucial control point in the SDN infrastructure. If a controller is down, then it collapses the whole network. There are many research studies on hybrid controller platforms, such as listed here. However, they are mostly logically centralized architecture, meaning that it makes decisions based on the network-wide state. Assuming all application on a network-wide state is challenged because synchronization is always an issue in real life. So we introduce a logically distributed controller, KANDOO. I don't know how to pronounce it, but I will just call it KANDOO. And this is the core of this presentation, so I will try to explain it slowly and clearly. There are multiple local controllers and a logically centralized root controller. Every controller has a view of the domain it is responsible for, and you can make decisions for it. In other words, communication between controllers within the tier is not allowed. If the root controller needs to install flow entry on the switch of a local controller, it pushes the request to the respective local controller. For software switches, local controller can be directly deployed on the same end host. Otherwise, deploy KANDOO local controller on the processing resource closest to the switch. In most cases, a newly arrived package in the switch only needs to undergo its corresponding local controller via OpenFlow protocol to exchange information. Less frequently, the local controller needs to talk to the root controller to fetch unknown flow or in general require a global decision. The root controller also retrieves statistical data from the local controller periodically for centralized model. Policy and business network update from the network application are also sort of common from the root controller to the local controller. In summary, local controller only talk to the root controller when it needs network-wide state. Application can subscribe event to controller, and root controller can subscribe to any local controller event. Here's a list of advantage of KANDOO SDN controller. First is load balancing because the controller bottleneck is shielded by local controller proxy. And it's easy to scale up and down because you can simply remove and add the local controller. And the system overall is fault tolerant because it prevents a single point of failure. And for performance, I'll discuss later. And so what is this? These are elephant on a grassland. But what I'm actually going from here is what's called elephant flow. And elephant flow are data sessions that take up significant amount of network capacity relative to other types of data session. So elephant flow connection takes more bandwidth. For example, Twitch streaming versus Twitter posting. So Twitch streaming in this case will be a elephant flow. And on the other hand, the Twitter posting or Twitter comment will be a mouse flow. So with that in mind, the experiment was conducted from some networking researcher from the University of Toronto to test out the performance of KANDOO SDN controller. using elephant flow detection as a methodology. The detail of how they set up the controller is ignored here, but you can look it up on the paper. What's important is that they found that a single KANDOO controller can reach a throughput of more than 1 million packet in per second from 512 switches using a single thread on an Exxon E7-4807 processor, with a closed data path to the switch. And from that, they also found that the central control channel consumption and the load on the control channel consumption and the load on the central controller are considerably lower for KANDOO, even when all the flows are elephant. The root controller is set up only be triggered when there's elephant flow detected in the local controller, and the event is pushed to the root controller to install new flow entries on all switches for the detected elephant flow. As a result, as you can see on the graph, the KANDOO root controller have way less traffic than normal open flow controller. And what's this? This is a control key in your hand. So from this implies that how developer implement KANDOO subsystem under the hood is in their total control. KANDOO is just a proposal of a logically distributed hybrid SDN controller architecture. For example, the root controller cluster can be orchestrated by Zookeeper to have a fault-tolerant distributed computation. Another example is the communication between the root controller and the local controller can use a publisher-subscriber messaging pattern such as a RabbitMQ. For that reason, KANDOO is a practically feasible hybrid SDN controller that can achieve high scalability, high performance, and high reliability. So SDN has been put into practice, no matter it is data center, mobile network services, or basically any enterprise network. The goal is to gain automation and better insight to make smarter network decisions. Here are some SDN vendors who has been working on SDN solution in the market. There are many other more, of course, including Cisco. And for example, Google and Amazon, they use SDN in-house with their own architecture. So SDN is such an incredible topic, and I wish it can really be on the final exam. And this is all my presentation. Thank you so much for listening.